Welcome to the course on 3G and 4G wireless mobile communication systems. We are discussing code division for multiple access, or we said that CDMA or code division for multiple access is a multiple access technology on which third generation wireless communication systems are based. Last lecture we looked at the fundamentals of how CDMA decouples or distinguishes the received signals of different users on the common air interface using different codes. We said that is possible through the use of orthogonal codes. For instance, I have here two codes C0, C1 which are orthogonal, that is their dot product or inner product is 0, and hence using such orthogonal codes CDMA can multiplex or enable multiple access of different users on the same interface. Last class we also saw that these sets of orthogonal codes, for instance C0, C1, C2, C3 look like random sequences of plus and minus ones, and we said such long random sequences can be generated using what are known as linear feedback shift registers or LFSR. A linear feedback shift register architecture consists of a set of registers. I take two outputs, combine them linearly. For instance, here I am taking xi minus 3, xi minus 4. I am combining them linearly, and then I am feeding it back as xi to the set of registers. Hence, this is a set of registers, there is a linear combination and then there is feedback. Hence, this is a linear feedback shift register, also abbreviated as LFSR. And the equation of this register, that is xi, is generated as xi minus 3 XOR with xi minus 4. So, the equation, defining equation of this feedback register or LFSR is xi equals xi minus 3 XOR with xi minus 4, and we were about tabulate the different states and the outputs of this linear feedback shift register. So, let us start with this lecture with basically going through the different states and the different outputs of the linear feedback shift register. But before I go with that, let me again illustrate that in this linear feedback shift register, the output here of this LFSR is xi minus 4. So, the xi minus 4 is where is the output of this linear feedback shift register. With that, let us discuss the output and the behavior of this linear feedback shift register. All right. So, I will write here 4 columns xi minus 1, xi minus 2, xi minus 3, xi minus 4, and xi is generated, remember, as xi minus 3 XOR with xi minus 4. Okay. So, this xi minus 2, xi minus 3, xi minus 4, they are also known as the state. So, this is also essentially known as the state of the linear feedback shift register. Let us assume that I am starting from the all 1 state, that is xi equals 1, xi minus 1 equals 1, xi minus 2 equals 2, xi minus 3 equals 1, and xi minus 4 also equals 1, and hence the output in this state is xi minus 4, which is 1. Now, remember, xi is xi minus 3 XOR with xi minus 4, both xi minus 3 and xi minus 4 are 1, hence xi minus 3 XOR with xi minus 4 is 1 XOR 1, which is 0, hence xi is 0. Now, in the next cycle, xi will go through the feedback register to become xi minus 1, xi minus 1 will become xi minus 2, xi minus 2 will become xi minus 3, xi minus 3 will become xi minus 4, and that defines the next state. So, we started from the state of all ones. The next state is 0, 1, 1, 1. The output in this state is xi minus 4, which is 1, and xi, which corresponds to the xi of this state, is xi minus 3 XOR xi minus 4, which is 1 XOR 1, which is again 0. Now we can again continue the same process, that is xi becomes xi minus 1. So, this will become 0, this will become xi minus 1 becomes xi minus 2, which is 0, this is 1, this is 1, the output is the xi for the next state is 0. Alright. So, continuing this fashion, let me fill out the rest of the entries. The next state is 0, 0, 0, 1, and xi is now 1 XOR with 0. So, xi is 1. The next state is 1, 0, 0, 0, and xi is 0. The next state is 0, 1, 0, 0, and xi is 0. The next state is 0, 0, 1, 0, and xi is, look at this, xi is xi minus 3 XOR xi minus 4. So, xi minus 3 XOR xi minus 4 is 1 XOR 0, which is 1, and this one will again go here to define the next state, which is 1, 0, 0, the 1 xi minus 3 becomes xi minus 4. So, this will become 1 and this xi is 1. So, at every state, please verify that we are, it is easy to verify how the next state is generated from the current state. So, at every state, please ensure that the calculations that we are doing correct. You can go through this table again just to understand, enhance your understanding. I mean, if you can do these computations by yourself, you will understand this better, how this LFSR or linear feedback shift register is functioning. The next state is 1, 1, 0, 0, and the output corresponding to this is 0. The next state is 0, 1, 1, 0, and the output corresponding to this is 1. I will continue on the next page. So, I will write xi, xi minus 2, xi minus 3, xi minus 4, and here I will write this as xi. So, the previous state is 0, 1, 1, 0, and the output is 1. This 1 will come over here. So, the next state is going to be 1, 0, 1, 1. So, the next state is 1, 0, 1, 1, and output and xi is 0. The next state is 0, 1, 0, 1, xi is 1. The next state is 1, 0, 1, 0, and xi is 1. The next state is 1, 1, 0, 1, and xi is 1. The next state is 1, 1, 1, 0, and xi is again 1. And now you can see xi will come over here, which will become xi minus 1, and the next state is simply 1, 1, 1, 1, which is the all one state. If you can go back to this slide, look at this. We started with the all one state and we are coming back again to the all one state. So, now we have come back to the state with which we have started. At this point, the linear feedback shift register and the outputs will again go through the same cycle that we have seen before, because we have again reached the state, the all one state that with which we have started. Hence, we have come back to that state. At this point, it will start repeating. In fact, no matter which state we start with over here, you can see if I start with, for instance, the state 0, 1, 1, it will go through all these states. Following all 1, it will come to the 0, 1, 1 state, and again it will start giving the same output. Hence, this linear feedback shift register generates a set of, it is periodic, the outputs are periodic, and essentially the output sequence, as we have said, Remember, we already said the output is nothing but xi minus 4, hence the output sequence, I am boxing this output sequence over here, the output sequence of this linear feedback shift register is this column of xi minus 4. That is, I am taking a single period of xi minus 4, calling this output sequence. Remember, this is also a pseudo noise sequence, or this is in other words a PN sequence. And why are we, again let me remind you why we want this PN sequence, because we want to generate codes that can be used for CDMA. That is, we want to generate these orthogonal codes that can be used amongst multiple users for multiple access. All right. So now let us first examine this linear feedback shift register. First, let us look at this. Let us count the number of states in this linear feedback shift register. The all one state is the first state, then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It goes through 15 distinct states before it starts repeating. Again, look at this, we started with the all one state. After 15 states, again we end up with the all one state. Now remember, the state has 4 different quantities, xi minus 1, xi minus 2, xi minus 3, xi minus 4, and each xi can take 2 different values. Hence, the total number of states is 16. The total number of states of this LFSR is 16. However, it only goes through 15 of the 16 states, that is, it does not go through every state. And why is that happening? If you look at this carefully, observe this, it goes through all states except the all 0 state. So let me write that down clearly. The LFSR, the linear feedback shift register, goes through all states except, and this is a big except the all 0 state. That is, it does not go through this all 0 state. So look at this, we have 4 registers corresponding to xi minus 1, xi minus 2, xi minus 3, xi minus 4. So if D is the number of registers, if D is the number of registers in the LFSR, then the number of states is 2 power d minus 1. Then the number of states is 2 power d minus 1. In this case, d equals 4, hence the number of states is 2 power 4 minus 1, which is 16 minus 1, which is 16. So in this case, d equals 4, hence the number of states equals 2 power 4 minus 1 equals 15. So the number of states is 2 power 4 minus 1, which is 15. Okay. Now let us look a little bit more closely at the all 0 state. Let us take xi minus 1, xi minus 2, xi minus 3, xi minus 4 as the all 0 state. Let us see what happens if this register is in the all 0 state. So xi minus 1 is 0, xi minus 2 is 0, xi minus 3 is 0, xi minus 4 is 0. Now if I look at the xi is xi minus 3 XOR xi minus 4, which is 0 XOR 0, which is 0. Now in the next cycle, xi will become xi minus 1 which will become 0, xi minus 1 will become xi minus 2, which is 0, 0, 0, again xi is 0, and then this will go into again the 0 state. Hence, if you start in the all 0 state, the LFSR continues to be in the all 0 state. So, it continues in the all 0. So, it is the LFSR becomes locked in the all 0 state. So, if it gets in somehow it gets into the all 0 state, it will never get out of the all 0 state. So, it hence the LFSR can never start in an all 0 state, and in fact, during the cycle it can during its period it can never enter the all 0 state also, because if it once it enters the all 0 state, it will never get out of the all 0 state. That is the reason the all 0 state does not. So, it visits all the states except the all 0 states, and hence an LFSR which goes through all states except the all 0 state is known as a maximal length LFSR. Hence, an LFSR which goes through all states except the all 0 state is known as a maximal length LFSR is known as a maximal length linear feedback shift register, and the sequence that is generated by this maximal length linear feedback shift register is known as a maximal length sequence. So, the PN sequence generated by the maximal length LFSR is known as a maximal length sequence. Now, in this case, as we have seen, it visits all states except the all 0 state, hence the number of states is 2 power d minus 1, hence the length of the sequence is also 2 power d minus 1, hence maximal length sequence is of length 2 power d minus 1. The sequence, consider if I have a linear feedback shift register with d registers, the length of the maximal sequence that can be generated is 2 power d minus 1. In the previous case, the number of registers was 4, hence the length was 2 power 4 minus 1, which is 15. Okay, all right. So, that is how long PN sequences are generated. Let us look at some properties. Of these PN sequences. The PN sequence that was generated was, let me write down that PN sequence, that is 1 1 1 1 0 0 0 1 0 0 1 1 0 1 0. So, the sequence that has been generated is 1 1 1 1 0 0 0 1 0 0 1 1 0 1 0. You can verify this from this table. If you take this outputs together, that is xi minus 4, and take them for one period, that is the PN sequence that is over here. Now, I have to map them to a voltage level. So, I will map 1 to a minus 1 and 0 to a plus 1. I am taking this information symbols 1 and 0 and I am mapping them to voltage levels, either plus 1 or minus 1. I am mapping 1 to a minus 1, I am mapping 0 to a plus 1. So, I will have the code that is given as minus 1, minus 1, minus 1, minus 1, 1, 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, 1. Alright, this is the code. So, given the PN sequence, I am mapping 1 to a minus 1, 0 to a 1 to generate the code. Now, let us look at the properties of this code. Let us count the number of 1s and minus 1s in this code. The number of minus 1s is 1, 2, 3, 4, 5, 6, 7, 8. So, there are 8 minus 1s in this code. 8 minus 1s in the code, and the number of 1s is therefore 15 minus 8 is 7. So, there are 7 1s or plus 1s in the code. Hence, what we can see is that this code is roughly balanced. Alright, the number of minus 1s and the number of 1s is approximately equal, except the number of minus 1s is 1 more than the number of 1s. That is what you would expect if you have a random sequence, and if you are computing the number of plus 1s and minus 1s, then you would find that because the probability of 1 and probability of minus 1 is approximately is equal to half, the number of 1s is approximately equal to the number of minus 1s, and that is what we observe here. The number of minus 1s in the code is simply 1 more than the number of 1s. That is the defining property of a PN sequence. So, let me write the property: the number of minus 1s in the code is always 1 greater it's always 1 greater than the number of 1s in the code. So, the number of minus 1s in the code is always 1 greater than the number of 1s in the code. So, this is the first property. So, let me label this. This is property now. Property 2 is also known as the run length property. Let me illustrate that property 2 here. A run is any string of continuous values. That is, if I have a string of 1 1 1, that is one run. If I have a string of minus 1 minus 1 minus 1, that is one run. So, a run, so let me write property 2. This is known as run length. This is known as run length property. A run is a string of continuous values. So, a run is a string of continuous values. All right. So, let us look at the runs in this PN code, pseudo random code of plus 1s and minus 1. I have a run, one run of minus 1s. I then have one run of 3 of plus 1s, that is the second run. I then have one run of a single quantity of one run of 1 minus 1. So, that is the third run. Then I have one run of 2 plus 1s, that is the fourth run. Then I have one run of 2 minus 1s, that is the fifth run. Then I have 3 runs of 1 minus 1, that is I have one run of 1 1, that is 6, one run of 1 minus 1, that is 7, one run of 1 1, that is 8. So, there are 8 total runs in this PN sequence. So, let me write that there are a total of 8 runs in this PN sequence. The number of runs a run is a continuous string of values. We counted the number of runs in this PN sequence and we are saying that there are a total of 8 runs. Now, let us look further at these runs. There is one run of length 4. So, let me now classify or categorize these runs as different runs. So, there are 8 runs, out of which there is one run of length 4, or basically out of all the runs 1/8. Remember, there are 8 runs, one run is length 4, which means 1/8 of the runs are of length 4. 1/8 of runs are of length 4. Out of these 8 runs, 2 are of length 2. Look at this, there is one run of 1s of length 2, one run of one run again of length 2, which is comprises of 2 minus 1s. So, there are 2 runs of length 2. So, there are 2 runs of length 2, which means out of the 8 runs, 2 runs are of length 2, which means 1/4 of all runs are of length 2. So, 1/4 of runs are of length 2, and also now I have, you can count here, I have 4 runs, 1 2 3 4 runs of length 4. So, there are 4 runs of length 1, which means half of the runs are of length 1. So, half, because 4 is half of 8, which is the total number of runs. So, half runs are of length 1. That is a very interesting property. So, half of the runs are of length 1, 1/4 of the runs are of length 2, 1/8 of the runs are of length 4, and so on and so forth. So, if I write this thing, half runs of length 1, 1/4 runs of length 2, 1/8 runs of length 4, and so on and so forth. That is, half of the runs are of length 1, 1/4 are of length 2, 1/8 of length 4, and then for longer PN sequences you can say 1/16 of the runs of length 8, and so on and so forth, and you can continue. So, this is known as the run length property of PN sequences. This, as we said, the name of this is the run length The earlier property that we have seen, that the number of plus ones and minus ones are balanced, is known as the balance property. We called it property 1, but that is also known as the balance property. The second property is known as the run length property of the PN sequence. Any PN sequence that is generated by the linear feedback shift register obeys this run length property. And the third property is the most important property of PN sequences, which is known as the cyclic shift property. So, let us look at the third property of PN sequences, property 3 of PN sequences, which is known also as the cyclic shift property. Now, let me write down again the same PN sequence that I had written before, that is minus 1, minus 1, minus 1, minus 1, 1, 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, 1. So, this is the PN sequence that we have, that is minus 1, minus 1, minus 1, minus 1, 1, 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1. Now, what I will do, so let me call this as code C0 of n. Alright, this is the code C0 of n. Now, what I am going to do is I am going to take this code and shift it in time. So, I am going to consider C0 of n minus 2, which is I am taking each chip of this code and shifting it to the right by 2 units. Remember, f of t minus t naught is a shift in time by t naught. Similarly, C0 of n minus 2 is shifting in time by 2 chips. So, here the shifted code will look like this, minus 1 will come over here, this minus 1 will go over here. I am writing it underneath. So, this is minus 1, minus 1, 1, 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, and I will take these last 2 chips and shift them to the front, because this is a cyclic shift. I am shifting cyclically, which is I am shifting by 2 units, and the last 2 chips I will shift to the front. So, in the front I will have minus 1 comma 1. Alright, so I have C0. So, what I have now is I have a PN sequence and I have a shifted PN sequence, cyclically shifted in time by 2 units. Now, I am going to compute the correlation of these 2 shifted sequences. If these 2 sequences, I define the correlation as 1 over n summation C0 of n C0 of n minus 2. That is, I am taking C0 n, which is what I have written down here, C0 n minus 2, which is what I have written down beneath. I am going to compute the correlation, that is, I am going to take the product chip by chip, summation, sum all the products, and then divide by n, which in this case is 15, because the length of the sequence is 15. So, let me first take the product. Minus 1 into minus 1 is plus 1, minus 1 into 1 is minus 1, minus 1 into minus 1 is 1, minus 1 into minus 1 is 1, 1 into minus 1 is minus 1, 1 into minus 1 is minus 1, 1 into 1 is 1, minus 1 into 1 is minus 1, 1 into 1 is 1, 1 into minus 1 is minus 1, minus 1 into 1 is minus 1, 1 into minus 1 is minus 1, minus 1, 1, 1. Now, let me add all these up. When I sum all these things up, so sum C0n minus 2, you can verify this is 1 minus 1 0, 1 1 2 minus 2 0, 1 minus 1 0, 1 minus 1 0, minus 3 ones minus 3 plus 2, this is minus 1. So, 1 over n summation C0n minus 2 is simply minus 1 over n, which in this case is minus 1 over 15. So, what have I done? Let me just recap it, because I went over a couple of steps. I took the Pn sequence C0 of n, I shifted the Pn sequence by 2 chips. I am computing the correlation with the shifted sequence, which is defined as C0n minus 2 summation over n divided by capital N, which is the total length of the Pn sequence. I have to compute the product chip by chip, add these products and then divide by n, which is 15, and I am saying that sum C0n minus 2 is minus 1. So, that correlation is minus 1 over 15, and you will find this is not unique to a shift by 2. If I take any shift other than the trivial shift, which is 0, 0 is no shift. So, if I take any finite shift, that is 1, 2, or even if I shift to the left, if I take minus 1, minus 2 and I compute the correlation will exactly be minus 1 over 15. So, the shift property states that the correlation for any shift other than, so the shift property that the correlation for any shift other than 0 is minus 1 over n. So, the correlation for any shift other than the trivial 0 shift is minus 1 over n. In this case, n is 15, the length is 15. So, the correlation is the correlation for the shift of 2 is minus 1 over 15. So, how about the correlation for any shift for the shift 0? We have not addressed that, but the correlation for shift 0 is simple. That is, for shift 0, the correlation is 1 over n C0n summation C0n into C0n itself, because the shift is 0. So, C0n into the shifted, which is C0 of n itself, which is 1 over n summation C0 square of n, which is now, if you look at it, each C0 of n is either plus 1 or minus 1. In both cases, C0 square of n is 1 itself. Hence, summation C0 square is nothing but 1 over n summation of 1, which is essentially n over n, which is equal to 1. So, now we have a much clear picture of the correlation structure. For no shift, it is perfectly correlated, that is, the correlation is 1. As soon as you have any shift that is other than 0, that is shift 1, 2 or minus 1, minus 2, the correlation falls down to minus 1 over n, and the larger the n, the smaller this correlation is. So, in fact, let me write that down here. Correlation of Pn sequence this is 1 if the shift equals 0, it is minus 1 over n for any other non-zero, for any other non-zero shift, the correlation falls down to minus 1 over n. So, if I draw this, if I represent this pictorially, at 0 the correlation is 1 and then it falls down to minus 1 over n for any other shift. So, the correlation looks like this. This is 1, at 0 the correlation is 1, at 1, 2 or at any other value it falls down to minus 1 over n. So, this is minus 1 over n. So, at 0 it is 1, outside of 0, that is for either correlation, that is for a lag, that is delay, that is positive or negative, it falls down to minus 1 over n, and this is the correlation diagram for a PN sequence. Okay, so, this is how the correlation structure looks for a PN sequence, and it is important to keep this in mind, because such PN sequences and such codes form the heart of every CDMA system. They are the key component of every CDMA system. Hence, it is very important to understand the properties of these PN sequences in detail. Hence, I urge you again to go back, take a look at the several properties that we have discussed in PN sequences regarding linear feedback shift register and the length of the sequences and the properties of the PN sequences generated by these LF linear feedback shift registers or LFSRs. Okay. Now, we will move on to studying some more properties of random sequences which are going to be useful to us, namely the cross correlation and the variance properties, so that we can model these sequences during our study of CDMA. So, let me start this discussion on random spreading sequences. So, I will first start with random spreading sequence. Okay. Now, let me consider a random sequence. A random sequence Ci for 1 less than or equal to I less than or equal to n, that is, I am considering a sequence of chips Ci for I 1 less than or equal to I less than or equal to n, that is, I am considering a total of n such chips such that each Ci is plus 1 or minus 1 with probability half, that is, each chip is either plus 1 or minus 1 with probability half. It is like tossing a coin. If the coin lands on heads, it is minus 1. If the coin lands on a tail, it is plus 1. So, each chip is plus 1 or minus 1 with probability half, and more importantly, each Ci is independent of another chip Cj. Each chip Ci is independent of Cj. That is, if I look at two different chips C1, that is C1 and C2 or C3 or C100, these chips are independent. That is, the random event that generates these two chips are event. It is like I am tossing a coin every time I want to generate a chip. All right. Now, I will consider two such spreading sequences, C0i, where C0 is a sequence, is C sequence which contains n chips, each chip plus or minus 1 independently with equal probability of half, and another sequence C1i also having the same property, that C1 also has chips which are independent and plus or minus 1 with probability half. So, I will write here these are of length n, that is 1 less than I less than equal to n, 1 less than I less than equal to n, and further C0 and C1 are themselves independent. Further, Alright, so C0 and C1 are independent, that is the chips of C0 have no relation to the chips of C1, that is they are generated, both these sequences are generated as independent random events. Alright. Now, let us look first at some properties. Let us start with a very basic property. Let us say I take any single chip, let us say I take any single chip of any sequence, let us say I take a chip of C0. What is the expected value of a chip of a sequence? Let us say I take expected value of C05, I take some ith chip, I ask you what is the expected value of this ith chip. You can see that each Ci is +1 with probability half, -1 with probability half, hence the expected value is nothing but half into 1 plus half into -1, which is 0. Alright, so the expected value, so it takes +1 and -1 with equal probability, so on an average its value is 0. The expected value is half probability into value, half into -1 probability into value, which is 0. Now let us ask this question, what is the time lag correlation of this chip sequence? For instance, let me take a chip sequence C0, correlate it with a shifted version of the same chip sequence. Alright, now this is, we are talking about a truly random sequence, we are not talking about a pseudo noise sequence, we are in fact talking about a truly random chip sequence. The idea is, for large sequences, the pseudo noise sequences behave as if they are truly random sequences, hence we are studying the properties of these truly random sequences. Alright. So let us ask, if I take a lag of k and compute the correlation, what is the expected value and what is the expected value of, or what is the second order moment of this. So let us start with the correlation. Let me define R of 0 0 of k, that is for some lag k, the self correlation of sequence 0 with itself as 1 over n summation C 0 I into C 0 I plus k. That is, I am looking at the self correlation of the chip sequence and the chip sequence shifted by k. Alright. Now, if I look at the average expected value of this, expected R 0 0 of k is expected value of 1 over n summation C 0 I C 0 I plus k. I will take, since the expectation operator is linear, I will take the expectation inside, that is 1 over n summation expected C 0 I into C 0 I plus k. Now, I will use a property that I have assumed before, which is I am assumed that each chip C I is independent of another chip C j. Hence, C 0 I here is independent of C 0 I plus k, which means if there are two independent random variables expected of x comma y, where x and y are two independent random variables, is simply expected x times expected y. Hence, I am going to simply write this as 1 over n sigma expected C 0 I expected C 0 I plus k, which is equal to 1 over n. Now, we have seen in the previous case that expected C 0 I is 0 for any chip, hence each of these expected C 0 I, expected C 0 I plus k are 0, hence this is 1 over n summation 0, this is 0. So, the expected value of this correlation for any shift k, remember this is a non-zero shift, k is 0. Now, let us compute something that is more interesting and more useful, which is what is the variance of this. So, I will define, so R 0 k, so R 0 0 square of k is nothing but, take two such terms R 0 0, take R 0 0 and take its product. So, R 0 0 k into R 0 0 k, that is summation over I C 0 I into C 0 I plus k into summation over j C 0 j C 0 j plus k. Alright, I am taking two R 0 0 terms, multiplying them with each other. These I and j are simply summation indexes. So, do not get confused with them, they are simply the same term represented by different summation indexes, and I will write them as a double summation as summation over I, summation over j C 0 I C 0 I plus k C 0 of j C 0 of j plus k. Alright, this is R 0 0 square of k. Alright, there is also a factor, I am sorry, there is also a factor of 1 over n. So, that becomes 1 over n square, and then that is also 1 over n square. Hence, expected value of R 0 0 square of k, which is the expected value, which is second order moment of the correlation at lag k, is nothing but 1 over n square expected, or I will take the expected value inside, summation I summation j expected value of C 0 I C 0 I plus k C 0 j C 0 j plus k. Now, look at this expression C 0 I C 0 I plus k C 0 j C 0 j plus k expected value. Now, if I is not equal to j, then these chips are independent. We said C 0 I is independent of C 0 of j, because any two chips, when I is not equal to j, the two chips are independent, hence the expected value is expected value C 0 I into expected value C 0 j and so on. However, if I equals j, then we have, that is the only term that survives, that will become 1 over n square sigma I expected of C 0 square I C 0 square C 0 square of I plus k when I equals j. So, when I is not equal to j, all such terms will become 0. When I equals j, we have something interesting, we have C 0 square of I C 0 square of I plus k. Remember, C 0 I and C 0 I plus k are both plus or minus 1. So, C 0 square I and C 0 square I plus k are both equal to 1, hence this product is 1. So, this will become 1 over n square summation of 1, which is essentially n over n square, which is 1 over. Hence, expected, let me write this down clearly over here, expected R 0 0 square of k is 1 over n. So, given two random sequences, first we have derived that expected R 0 0 k is 0, and the second moment expected R 0 0 square, that is the variance of the shifted correlation, is 1 over n. it decays as a function of n. As the length n increases, this variance goes to 0. This is an important property when we study the behavior of CDMA system. So, I urge you to again revise these concepts. I will end this lecture over here, and we will continue starting with this in the next lecture. Thank you very much.